Let's continue our discussion of file permissions as well as set GID, UID, and the sticky bit. We'll pick up where we left off with the sticky bit. And we told you that the sticky bit allows you to create directories where users can place items such as /temp that other users will not be able to remove inadvertently or purposefully. With that said, with the sales directory, let's take a look at it to see whether or not we've altered the bit. It was lsld /sales, and it doesn't have the sticky bit. However, it has set GID set so that users' files will be applied with permissions that we have set at the top level directory, which includes the sales group. To set this directory as sticky, we'll change mod 3777, which will permit all users' rights to write to the directory. So task is to set /sales using sticky bit and test. So step 1 will be to, of course, change mod 3777. Now just a quick note about the prefix 3. Generally, when we apply permissions to files and directories, we omit the first bit. So usually that means a 0 is here or understood or implied. But in the case of set UID, GID, as well as sticky bit, we turn on the leading bit. So 3777 enables the leading bit such that it's sticky. /sales, and we'll follow that up by lsld /sales to ensure that is that the sticky bit has been set. Let's give this a try. Now the sticky bit is set, which means users who write files and or directories to the sales directory will not have them removed by other users. So with that said, we should test it as two non-privileged users, Linux CBT and student 1. So let's navigate into sales where we appear to be. We're just pwd, we are. And I will sequence 1,000,000 Linux CBT test.sticky.1,000,000.text. This will complete quickly, and then we'll lsltr to examine the contents where you see the file's been created with similar permissions to the previously created file. However, because the group bit, that's lsld sales, because the group or set GID bit is set, the permissions are still applied as such. So if you want to effect this change to drop set GID, you need to turn the permission off. So first we'll change mod 777 /sales, then lsld /sales. It's now set to the appropriate permissions. Then we'll 377 the directory and re-examine the contents of sales. So in other words, sticky and group ID bits don't work well together. And let's lsld. Now it's set again with set GID. So let's apply this to the marketing directory, which is a clean directory. Let's see if it's created at the root of the file system. And it isn't. So we'll make directory marketing followed by change mod 3777 marketing followed by an lsld marketing. And we'll examine the contents one more time. We'll lsld marketing. And there we see the bit is set exactly how we want to. Optionally, you may use change mod +t to apply the sticky bit. So, or change mod +t /sales. Let's take a look at the sales directory. We'll try that as well. Change mod +t sales followed by lsld sales. And there you see the sticky bit is applied. So now, as a non-privileged user, Linux CBT, let's navigate to marketing, and we'll do the same for sales. We'll sequence 1,000,000 to Linux CBT test.sticky.text. And we'll everyone else see that the permissions are set differently. Instead of being owned by Linux CBT and sales, the file is owned by Linux CBT and Linux CBT. Standard Red Hat Linux permissions, user principal, group principal, permissions are set to 664, or read-write for the owner as well as group owner, and read for everyone else, which means everyone else will be unable to make changes to entries created by Linux CBT. And ditto for the student 1 user. Let's find student 1's shell. We'll su here as student 1. Then navigate to the marketing subdirectory, and then use sequence to create student1.test.sticky.text, and then examine the contents once it's completed, where you see the permissions have been written. So now the user Linux CBT will be unable to remove student 1's entry. Student 1 will be unable to remove Linux CBT's entry. For example, if we attempt to remove RF Linux CBT, it fails. We can take a look at it, we can examine it, but we can't remove it. So this is a way to create a directory where multiple users share the directory but cannot remove or clobber each other's files. So that's what's meant by the sticky bit. If you find that 377 still sticks the group ID bit, then use change mod plus T after having applied 777. So you could do change mod 777 sales followed by change mod plus T sales, and then you'll see that the sticky bit will be set just like the temp directory. And what you want, the desired result, is as follows: that you see read, write, execute for owner, group, and everyone else, but in the last bit where you expect to find an execute, you see a T indicating that the directory is sticky. Super. Now let's move on. We want to discuss symlinks. Symlinks are important. There are two types. Symlinks provide shortcuts to files, which includes directories. But they're more than just shortcuts as you may be accustomed to them within the Windows environment, in that you can link to the same inode or hard drive location using the same or different names across your file system. So they provide more dynamic features than a typical shortcut. A shortcut provides a way to access an item within Windows. With a symlink, for example, you can provide a shortcut, you can provide an alternate name. The OS keeps a count of how many times the item has been linked. And if you hard link, you're actually referencing the hard disk location and not a file location as you typically do in Windows. So in Windows, when you create a shortcut is really a pointer to a file which leads to a disk location. Within Linux, the symlink, in particular a hard link, is really a pointer to the hard drive location. Additionally, symlinks provide alternate ways of running programs, such as egrep, grep. For example, when we execute which egrep, we see that it's located in bin. But when we actually examine the contents of bin egrep, we see that it isn't a standalone file. It is a symbolic link to grep. It's an alternate way of calling grep. Whenever grep is called as egrep, it knows to turn on its regular expressions engine. So this is yet another feature application of symbolic links. So it provides shortcuts to files, including directories, and provides hard links to inode, which are basically hard drive or file system locations. So let's begin by discussing soft links. To create a soft link, which is analogous to a shortcut in the Windows environment, the usage is as follows: ln followed by -s, lowercase s, to indicate that it's a soft link, followed by the source file or directory. And whenever we list file, we tend to also mean directory, so keep that in mind. Within a Linux environment, a file represents multiple types, including a standalone file, a directory, which is a container for multiple files, and other types of files such as block, character, hard drive, so on and so forth. So source file followed by target. This is the syntax that's used. So in the case of grep egrep, the symbolic link is created as grep being the source and egrep being the target. And we can link to pretty much anything we have access to in our system. So let's navigate to a simple shell for Linux CBT into Linux CBT's home directory and begin this process. To make things simple, we'll navigate into test.rh5, which is a cleaner directory, and create a symlink. Supposing we wanted to symlink to our recently created Perl script, regextest.pl, but we'd like to call it something else. So we'll go ahead and ln-s, since it's in the current directory, we could indicate /regextest.pl, and then we may call it something entirely different, such as lastscript.pl. Totally different name, symlink. Let's go ahead and try to apply this from the test.rh5 directory and examine the results. An echo of the exit status returns cleanly, and when we LSLTR, we'll see that lastscript.pl indeed points to /regextest.pl. So we can now invoke regextest.pl as lastscript.pl by executing it as follows: /lastscript.pl, which expects a match, of course, in order to perform its magic. So here's an optional way of calling regextest.pl. Now there's a quick note regarding soft links. Soft links may span multiple file systems / hard drives, whereas hard links, that is, may not span multiple hard drives or file systems. And that has to do with the linking to the inodes, which may be duplicated across file systems. Soft links can span file systems. Now, so far we've created a simple soft link within the same file system. And regarding the enumeration of the contents of the directory, if you turn on the inode option, you'll see that lastscript.pl references, or has its own inode, that is. So each soft link maintains its own inode, and it's a small number of bytes, 14 bytes, which points to a larger file that's 787 bytes. Notice, however, that the symlink count isn't increased as a result of creating a soft link. Let's note that as well. Symlink count is not increased when using soft links. So which means if you remove the source file which soft links are premised on, then you'll simply have broken soft links, like broken shortcuts in Windows. If you have a shortcut on your desktop pointing to a file somewhere on one of your hard drives, if you remove that source file, then the shortcut is no longer functional. But that is not the case with hard links. Now we turn on the I option to point out that when you create a soft link, it ends up having its own inode. An inode is a representation in the file system that maps to a hard drive location. But when you create a hard link, it wears the same inode as the source file. Now regarding this regextest.pl script, if we wanted to link it in a different file system, we simply use ln with the -s command. For example, since the script is a small file and a symlink is a soft symlink is very small, supposing we wanted to create a link to regextest.pl in a different file system, the boot file system, since home is beneath root. Well, we'd simply, providing we have enough permissions, as let's say the root user, so let's drop from the student1 shell, navigate to the boot file system, then execute ln home Linux CBT test rh5 regextest.pl and optionally specify a new name. If we're happy with the name, then we just indicate a dot to indicate that it's to be linked to the current directory. So let's just copy this command before we execute it and place it in our notes along with a brief description describing what it does. So to, let's indicate this will symlink, soft linked of course, to the boot file system, proving that you can symlink or soft link across file systems. We'll echo the exit status and it's clean. Let's LSLTR, and there you see a link to regextest.pl. If you don't indicate a new name, it simply inherits the name of the source file, which means from this file system, the boot file system, we can execute regextest.pl, and it'll run just like anything else. We'll give it a string, and it performs whatever it's supposed to perform, the pattern matching. So you can symlink across file systems. Remember, /boot is a 100 megabyte file system independent of where home's located, which is within the root file system, which is 35 gigabytes. So symlinking, straightforward. If you want a symlink as a different name, that's straightforward as well. Just change it to a different name, such as test regex test.pl. And now when we take a look, we'll see two links. Both are here. And if you look at the source file, which is beneath home, and we can use tilde to explain Linux CBT's home, test rh5, regex test.pl, notice the symlink count, or the hard link count, is still at 1, indicating that only the file beneath home Linux CBT test rh5 is linked to the inode. There are no additional hard links, which means you can remove the source file, and what ends up happening is you'll end up with broken symlinks. Ditto if you rename the file. So if for some reason you need to rename the source file, you will break your symlinks. Let's take a look at that. Back to Linux CBT's home directory. Let's move regextest.pl to regextest.pl.old. We'll just tack on a new suffix, then lsltr. Notice that this symlink is broken, and if you attempt to run it, it will fail. It doesn't even allow you to run it because it's no longer valid. And from the boot file system, if we lsltr, both will be broken. It turns up in big red. So let's just note that as well. With soft links, if you change the name or location of the source file, you will break all of the symlinks, or soft symlinks. Keep that in mind. Very important. Now with that said, let's discuss hard links. Main feature of hard links, the ability to reference the same inode/hard drive location from multiple places within the same file system. In other words, hard links cannot be made across file systems, but provides a means to publish an item throughout your file system using perhaps the same or different names. Let's fix the problem that we created here from Linux CBT's window by moving regex, that is, test.pl.old to regex test.pl. And when we lsltr, you'll see that the symlink is no longer broken, and we can now execute it with whatever values, and it works. And ditto for boot. Boot has been restored. If we lsltr, it's no longer red. So whenever you see red colorize in your main terminal window, it means that there are broken symlinks. Now we can hard link to the file that we've soft linked. There's no rule or facility or anything preventing us from doing so. Again, it provides the ability to reference the same inode, which means if you remove one instance, you don't trouble the others. So it's more flexible than soft links in that regard. So to create a soft link, or a hard link, that is, instead of a soft link, just don't use the -s option. So ln source target. For example, ln regex test.pl to a new name, let's call it test hard regex test.pl. This creates a hard link. Let's give this a try. We'll echo the exit status and then lsltr, where we'll see the test hard regex test.pl. Also notice that the counter for the links to the source file has increased, or to the inodes, that is, represented by regex test.pl, has increased from 1 to 2. And for each hard link you make to a given inode, it causes an increment, or it increments the hard link counter, or increments the link counter or hard link counter by 1. So now we've referenced it as test hard regex test.pl. What this also means is if we remove regex test.pl, has no impact on test hard regex test.pl. Let's try that out. It will, however, break the soft link. So let's copy and remove RF, this file, and then lsltr, and you'll see the soft link is broken, and ditto for the boot file system. The soft links there will be broken. However, the file that we created some videos ago still remains. If we execute test hard regex test.pl followed by its desired input, you'll see it works because it references the same inode. You can confirm it by lsltring with the I option and just confirming the inode that you see, and it's set here to 1,507,436. So it's still the same file. And if we were to subsequently move test hard regex test.pl to simply regex test.pl, then the symlinks, the soft links that is, will no longer be broken, providing we provide the right name. So we missed something here, we'll move regex test to simply regex test.pl. That should do the trick. And now it's linked again. And if we confirm the inode, you'll see it's still the same inode, 7436. Hasn't changed, still the same hard drive representation. Now how about trying to hard link from a different file system? As we told you, would not work. So here we are, we're within boot, which is a different file system. If we attempt to hard link, which means we don't use the -s option, from home, Linux CBT, test RH5, regex test.pl to here, tells us you cannot create a hard link, invalid cross-device link. And that is because each file system, root as well as boot, maintains its list, its distinct list of inodes which are likely to be duplicated. Inodes are simply numerically labeled and can easily be duplicated. For example, if you have two partitions that are at least the same size, so boot or root is at least the same size as boot, then you're going to have double inode numbers, and that is the problem behind hard linking across devices, because the OS would not be able to keep track of the proper mappings between your hard link and the true underlying data. So you can't link across file systems, but you can hard link within file systems, and it provides a way for you to represent something to different people. So you may have an item in SBIN that you'd like to make available to a user's directory. For example, let's go back to Linux CBT's home directory. We know that grep is beneath the bin directory. What if we wanted our own hard link to grep? You could ln bin grep to the current directory, and we'll just call it Linux CBT grep, and it creates it for us. Now we have our own version of grep in this directory. And now when we lsl bin grep, you'll see that the counter is up to 2. Remember, egrep is a soft link to grep, so it doesn't send up the counter. And when we execute Linux CBT grep from the current directory, it behaves just like grep. If we remove rf Linux CBT grep, the counter for the original file, grep, returns to 1, and we're back to normal. So hard linking provides a way to re-represent or represent items throughout the same file system. And that's really all there is to it. It's not complicated whatsoever. Now let's move on to another file system feature. That's the ability to limit users' usage of disk space. And we do so using quotas. They're straightforward to implement, but it requires remounting your file system with quota support turned on. So, the features are self-explanatory. However, we'll list a couple of them. You can configure them. Well, first and foremost, quotas limit disk usage. They're also tied to file systems. So you set quotas on a per file system basis, meaning they're set on a per file system basis. 3, quotas within Red Hat Linux, or Linux in general, since it's supported by the kernel and not Red Hat Linux per se, can be configured for users or groups. So you can set quotas up for users and or groups when you define your quotas after you've provided support for your file system. And again, you can use it to limit disk usage. The limitations on disk usage can be indicated using blocks or inodes. So you can indicate, for example, that a given user and or group has access to a set number of inodes, which translates ultimately to a set amount of storage, or to a set number of blocks. And depending on how your blocks are configured will determine how much storage is available to the user. The quota software must be installed. The package is actually quota RPM, so you should check to ensure that it's installed, and if not, install it. The default installation of Red Hat Enterprise Linux includes the quota package, but from the shell, simply execute RPM query all grep quota, and you'll see the package return as quota followed by its version if it is installed. So what are the steps to enable quota support? So steps to enable quota support. And this works for other distributions as well. In fact, many of the things we're covering works across distributions and aren't specific to, let's say, Red Hat, SUSE, Debian, Ubuntu, or any of those distributions. This is just basic Linux, general Linux knowledge. First and foremost, step 1, enable quota support per file system in etcfs tab, so that when we remount the file system or systems, quota support is provided. So we need to turn on quota support. It isn't turned on during installation. The option isn't provided during installation, unless you configure it through advanced configuration, where we're able to tweak the settings on a per file system basis, but generally you're unable to set it up during installation. Now the way this works in etcfs tab is as follows. You find wherever the default section is for the file system and append the support that you'd like. There are two types of support, user and group quotas. So if you want user quota support, indicate user quota and group quota. It's a good idea to turn both on and then determine once quota support is enabled which one you'd like to implement. Chances are you may implement both. Second step is to remount the file system or systems, depending on where you'd like to provide quota support. In our case, it's only the root file system, since boot is only used by the kernel in the operating system. So once we've remounted the file system, and we do so using mount-o remount, and for this system it will be the /file system. After we've remounted the file system, quota support will be available. We then create a quota database. Each file system maintains a database of quotas. So we create quota database files. And then we generate disk usage tables. We do so by performing the following steps. Quota check, CUG, which will create the files and applies to users and groups. And we also check the quotas using quota check again, but instead of CUG, AVUG, which checks the quotas for users and groups. After we've set up the quota databases, we assign quota policies. There's a program known as edQuota, which allows you to edit quotas. We execute edQuota, so the fourth step is to assign quota policies. This is where we actually determine what the quotas should be on a per user or group basis. We do so using edQuota, followed by perhaps a username. So if we wanted to limit student 1 or Linux CBT's usage, we'd indicate edQuota Linux CBT or student 1. When we do so, we're propelled into an interface where we can determine, so this allows us to set blocks, inodes, soft as well as hard limit. So once we use edQuota, we get to set the total number of blocks, the soft limit, this is where warnings start to occur for the user, and the hard limit. So if you set a soft limit, for example, of 10 blocks and a hard limit of 20 blocks, after the user has consumed 10 blocks, they'll be warned, but will still be allowed to write to the file system. When they hit 20 blocks, however, they will no longer be able to write to the file system. Now, to check whether or not a quota or the quotas are in place and the usage for an existing quota or for existing users in place, you can use the quota command. So check quotas. We can do so using quota username or even group name. This will confirm existing quotas. Now, it seems like a lot of steps, but it really isn't. Again, to recap, we enable quota support per file system. For this Red Hat Enterprise system, we have one file system that's of interest. That's / or root. So let's move forward with that. We're going to do so via etcfs tab. And we need to do so from the root shell, because otherwise we will be unable to save changes to etcfs tab. As you can see, the permissions are read-write only for root. So nano etcfs tab will find wherever the root file system is right here. We'll then indicate after defaults user and group quota support. So comma user quota, group quota. Now, since the nano editor wraps lines, be sure to bring everything back to the same line, to the first line, including the last two columns, which have 1 and 1 in them for the order in which the file system should be brought up and checked. So we've added defaults, or two defaults, user quota and group quota support. So that takes care of step 1. Step 2 is to remount the root file system, which doesn't always work, by the way. If it doesn't, the right way to do it then will be to reboot the system. So a mount, remount, / will attempt to remount the root file system. It's remounted. So far, so good. Doesn't appear to have been any problems remounting the file system. And also notice we've checked that user quota and group quota support has been enabled by using the mount command. Perhaps we should just stick that in. After remounting, use mount to confirm that user quota and group quota support is enabled, or are enabled. And we saw it in the output. So now that we know that both quota types are supported, we need to create the quota database files and generate the disk table usage. So we want to quota check CUG, and this will apply user and group quotas to the root file system. And we need to do it for root. We left out the root file system. We need to indicate the file system, because quota check can be used or applied to any file system. Let's move forward. And this tells us that it cannot remount file systems mounted on root, read-only, so counted values might not be right. That's not a problem. We can always adjust the quota values later on using quota check. The bottom line is we were able to run the program quota check. Now, whenever this error is thrown, it's a good idea to take its advice by using the M flag. The M flag forces the check of the file system, which ultimately creates the quota files for user and groups, meaning the quota database files. So if you rerun quota check with the M option turned on, this forces a check of the root file system. And what it will ultimately create are the two files, the two database files containing the usage. Also, quota check is a program that you'll want to run from cron on a recurring basis to update the quota usage throughout the day or throughout the usage of your server or Red Hat Enterprise system, such that if users are in violation of your policy, they'll be denied storage access. And that's quite easy to set up in cron to basically run a check several times a day. But besides that, it's a good idea to force a check and have it create the files that are necessary. And once the files have been created, we can check the quotas using the AVUG option, which is what we'll be doing next. Once we've confirmed the quotas are in place, the support that is, then we'll set up the quota policies using ed quota. Now you see this is finished, and if we lsltra /, you will see two files, aQuota.user, aQuota.group. These are the two quota files. So we should just note that. We'll just throw in the M option as well. This creates aQuota.user and aQuota.group. These are the important files, or GROUP. Now let's move forward with confirming and it tells us again that we should use the M option. So let's go ahead. Now it's going to scan, it's going to go through and check. This will check quotas throughout the file system. And once we've checked the quotas, this is just standard fare when setting up quotas, we'll then assign quotas on a per user basis. Currently we have no quotas in place. But this will scan through every directory and every file on the file system to determine utilization. It's a way of tallying up usage. In other words, there are files that are owned by root, Linux CBT, Student1, and other users, bin, other system users. QuotaCheck is going to create that table of information in the quota database files. So here you see it says it's checked 9685 directories and 107,315 files. We're now ready to assign quotas using ed quota. So let's move on to that next step. We want to set quotas, let's say for user Student1. Let's take it to the shell. We'll clear screen, reset the buffer, give us a nice clean buffer. By the way, you should set quotas as the user root. You will not be able to make changes as a non-privileged user. So either as root or root equivalent. Now notice we were propelled into the VI editor. If VI is not your desired editor, and it generally isn't mine, quit it using Shift:Q and then export the editor variable, setting it to nano. So we'll export editor, setting it equal to nano. Then we run ed quota Student1, and this will set you up in nano. So let's just make a note of that. Export editor equal nano to have ed quota default to nano editor, which is an easier editor to work with. So with that said, here's a layout of the important fields. We can stretch this out to try to get it to fit, and you'll see what we can actually set. So in the first column we've got file system, and here you see the disk quota usage for user Student1 for UID 501, the file system that it applies to, the blocks 13,504, soft and hard limits, number of inodes, and so on and so forth. We can stretch this out so you see the remainder of the columns. It terminates with soft and hard for inodes. The soft and hard that you see here applies to blocks. So you can set either soft and hard limits for blocks or soft and hard limits for inodes. Now we should also note that the number that you see here, 13,504, represents the current number of blocks in use by the user Student1. So when setting your soft and hard limits, they need to be at least what you currently see for blocks that are in use. So the blocks column represents the current usage. So set it higher than what you currently see, unless of course you want the user to clean up some of the existing space, which you probably wouldn't want to do, as it would cause the user to be unable to write items until they clean up. And same for the soft, or for the inodes. The 8 that you see here represents the number of inodes that are in use by the user. And you can confirm it, of course, by consulting the user's home directory. And if we were to SU in, for example, let's open a new shell, and we'll SU in as student 1. Try it again. Navigate to the home directory. And if you take a look at each of the files occupied by the user, even for hidden files, you can actually see the 8 inodes that are in use by the user. These are the files and the inodes that are in use. So again, the report tells you as such, and you can set soft and hard limits. Now by default, if a 0 is indicated, it means the user has no limit for any of the items. So for soft as well as hard blocks, the user can write until the file system's out of space. And ditto for inodes. So 0 usually means that the user has no limit, or group has no limit on storage, whether representing the storage as blocks or inodes. Again, if you want to limit the blocks, perhaps we'll set this to 13,600 for soft and 14,000 for hard. Then do so, and ensure that you bring the other items up to the same line, so it's all on one line, as Nano tends to wrap the items. So now, in the case of this user student 1, once we've applied the limits, if the user attempts to create a file that exceeds 14,000 hard blocks, it'll fail. If the soft limit is exceeded, then the user will still be able to write up to the hard limit. But there is also a way, using ED quota, to modify the amount of time that the quota system will allow the user to exceed the soft limit for either inodes or blocks. Using ED quota-T, you can indicate a time frame that the user has to clean up and get below or fall below the soft limit for blocks or inodes. But set one or the other, not both, either blocks or inode usage. When finished, Control-X to save the changes. This commits the changes to the new file, or to the temporary file, that is, which then subsequently commits the changes to the database file on a per file system basis. Again, the files are located in the root of the file system as quota group and quota user, with quota user recently being updated. But these are binary files. ED quota prevents us with a text-based interface and then writes the binary equivalents to the appropriate files, quota user or a quota.group, respectively, depending on the quota that you've manipulated. You may also confirm the quotas that are in use by a given user by using quota, the quota command followed by username. So for example, quota student 1 returns the usage information for that user. Go ahead and execute that from the shell, and it tells you everything that we saw with ED quota, including our changes. So here we see the soft limit is 13,600, hard 14,000. So now, as student 1, let's attempt to write a big file in our home directory. We'll clear screen, reset the buffer, and then use sequence to write a file that contains 10 million entries, calling it 10 million.txt to see if this will exceed the quota. It may not. We'll see momentarily. And so we'll continue to write the file. And again, you can update your quota information using quota check to scan the file system using AVUG, which checks for all users in all groups. And that is a process that you should place into cron to run multiple times per day. So note, place quota check AVUG in etc cron dot star, such as hourly daily, etc., whatever fits your schedule, to ensure that quota information is updated frequently. Now we're able to write the file, 10 million.txt, which is 109 megabytes. Let's rerun quota check for the user to see what's currently in use. It's still 13504, which means the stats have not been updated. So let's execute quota check, AVUG. And it needs to be forced. This will scan through the full file system and update the usage in the appropriate tables, the aquota.user as well as aquota.group files. And then when we rerun quota followed by the user's name or group name, we'll see the updated information. And the process is complete, so let's rerun quota on the user student 1. And now we see that the user is using more blocks with the asterisk indicating that the user has exceeded the quota. In this case, it's now at 124,748 blocks by virtue of creating that 109 megabyte file. The blocks are measured in 1K increments, which is why we're now using so many blocks. And the asterisk indicates that we're over the quota. And if we attempt to continue to write data, let's write a new file. We'll call this 10,002.txt. We've exceeded, of course, the soft limit. And now it's writing that new file to the disk. And the limits have not been enforced, but we are over. We've exceeded the limit, certainly. And now the second file has been created. Now LSLTR will show us those two files, and an updated quota check will return that we're using more of the storage. We may also report on the quota using rep quota -A. This reports the usage per user and tells what's currently in use. So for example, we see a plus for the user student 1 indicating that we've exceeded the soft as well as hard block limits, and there's a grace period of 6 days, after which point the OS will not allow us to write any more information beyond our soft limit. Again, this can be updated using edquota-t. This will allow us to change the grace period for blocks as well as inodes, whereby which the enforcement of the quotas will take place. So for example, time units may be in days, hours, minutes, or seconds. So we can say, for example, 1 hour, 3 hours, 6 hours, or days, minutes, you name it, to determine how we'd like to enforce. But as it stands, many days can go by before any sort of enforcement, giving users time to clean up. But again, the rep quota utility is a great way to report on usage. So report on usage. Again, you're going to use this as your information gathering tool, rep quota that is, to be able to determine who's using the storage on your system. So this reports on usage in a nice tabular form, which you can then take and use to inform your users that they're over their limits. So for everyone else, there are no limits except for student 1. You can set it on a group basis if you'd like. Just use the edquota-g command for a group. So for example, edquota-g, and let's modify sales, for example, sets up an interface for sales. This tells us sales is currently using 20,224 blocks, and we know that sales has written primarily to the /sales subdirectory. LSLTR, human readable, tells us that it's using sales that is roughly 20 megabytes, and when you convert that out to 20,224 1K blocks, then that's about 20 megabytes. And we should just note that as well, just in case you need to know. The blocks are measured in 1K increments, i.e. 20 blocks, or 20,000 blocks, is roughly 20 MB or 20 megabytes. So that gives you a sense for how to limit using blocks of cores. So in this case, sales is using about 20 megabytes, which seems to add up to what we see in the sales subdirectory, which we could limit by placing hard and soft limits and adjusting the time with which the enforcement goes into place. So that's a little bit about using quotas. Again, to recap, there are multiple steps to get quotas up and running. You want to enable it on a file system basis via FS tab, remount the file system, use mount to ensure that user and group quota support is turned on, create a quota database, force it using the M option, tally up usage using quota check with the M AVUG option. This will scan the file system to determine what's currently in use. Assign quotas for users or groups. You can optionally edit using your nano editor by exporting the editor variable. And you can check quotas using quota as well as the user or group's name. You may also report on quota usage using rep quota. And to keep your quota information up to date, place quota check AVUG, and if you need the M option, stick it in there, into one of the cron files to cause it to run once daily, hourly, monthly, weekly, so on. And again, roughly 1K blocks are used, or 1K blocks are used, and roughly 20,000 blocks would be equivalent to 20 megabytes, 10,000 blocks equal to 10 megabytes, so on and so forth. So if you want to limit a user to a gigabyte, then it would make sense that 1,000,000 blocks would do the trick. So that's a little bit about quotas. Let's move on.